So today I will present my work on multimodal representation learning with deep generative models. The part of this work is from my PhD at TU Darmstadt in Germany. And towards the end, I will also present some of the work that I did at University of British Columbia along with my students. Let's delve right into it then, right? So to begin with, what is multimodal, right? Like we hear a lot about multimodal learning, multimodal foundation models, but it is important to first learn what is multimodal, right? So multimodal in artificial intelligence, multimodal learning refers to machine learning models that can cater to representations from diverse modalities or domains like vision or natural language. And these days, audio is also very popular. Multimodal distribution, on the other hand, represents a probability density or mass function which has multiple peaks, unlike your standard Gaussian, for example. And in my research, we cater to both aspects of multimodal representations, that is, from different domains, as well as with different modalities in terms of peaks, which represents complex distributions, for example, at the intersection of vision and language, as well as within the image distribution, like complex imagery. Motivated by the observations that humans can solve complex tasks, such as describing what they see or recognizing objects that they have never seen before just by the textual description. That is where this research domain of multimodal learning prospered, and the goal was to leverage information from both visual and textual sources for scene understanding. The applications of this span various tasks, and the very popular among them are retrieval. For example, where given a text, you retrieve images which have some similar semantics with a high semantic similarity score, for example. And similarly, for a given image, you can retrieve texts which have similar semantic similarity. Yet another task is that of image captioning, where given an image, you want to describe the contents of the image in natural language. Visual question answering, where given an image and a question about the image in natural language, the goal is to produce the correct answer, but also again in natural language. So you see how there is an interplay of different modalities in terms of input and the output. Moreover, when humans use only perceptual cues, once they have recognized, for example, a giraffe in this scene in a park, right? In a very different setting, they can also recognize the giraffe in, for example, a zoo, in a wild scene, right? So we want to instill this information also in our AI models, that we are able to recognize objects across scenarios in the real world. What does this imply? In computer vision, tapping into the information acquired from this complex image data, it finds applications in image synthesis. I apologize for the image synthesis that I have. This is a very old, when GANs were new, right? So these days you can generate very high quality image, but this is the standard cipher images that you could generate not so long ago using your state-of-the-art GAN models, right? And it also finds applications in tasks such as image super resolution, where the goal is to recover your high resolution imagery from the low resolution images, right? So that is where you need these to understand what these image distributions look like. Now, for learning multimodal representations, it is desirable that you can combine information such that the machine learning algorithms can capture the concepts in the cross-domain settings or even in the single domain. In my research, I formalized this through a probabilistic modeling framework, which we can categorize into deep generative models, right? So what are these deep generative models? They aim to approximate the data distribution from the observed data under some parameters. Here in this slide, I denoted by theta, right? And these theta parameters, when learned with a deep neural network, give us a deep generative model, right? And they have been leveraged for various fundamental tasks, such as density estimation, where you compute the bits per dimension. You can tell how likely that data point is for the distribution, for image synthesis, for generation of synthetic data in speech, imagery, medical images, you name it. We have applied it, right? And then the range of applications, once you learn this underlying distribution, you can apply it to various downstream tasks, such as image super resolution, or even in the physical sciences, such as in molecular optimization, right? So, such as the vast application and the dynamics of these deep generative models. Popular generative models include, you all have heard of it, I guess, but let's just go through it for completeness. So they include GANs, generative adversarial networks, which implicitly learn the data distribution from noise through a mapping through a generator discriminator framework that you're familiar with. Then there are variational autoencoders, which are explicit models in the sense that they approximate the data log likelihood of the data distribution, right? Typically through an evidence floor bound. And then there are exact inference models, which estimate the exact log likelihood of the data. So there is no evidence flow about, but there is a direct mapping from your base distribution to your target distribution. So these are the types of generative models. And in my research, I built upon these deep generative models for joint modeling of images and texts, and also for complex imagery, but we won't go into the image part today. We will mostly focus on image and text. Now, what are the challenges when you want to learn these cross-domain representations of images and text? Now, when you look into purely supervised approaches, the original structure of each image or text distribution is lost when you have a supervised loss. So they learn representations such as similar image and text, the data point, the supervised example, they're close to each other, right? But then, for example, in the very popular COCO data set, right, you do not have similar matching image pairs. So you cannot preserve the image level similarity or the text level similarity when you do the supervised approaches. Thus, the semantic similarity within each domain is not preserved in the embedding space when you want to learn the joint representation. It is challenging to develop a structured latent space where similar images are close to each other, similar texts are also close to each other, as well as similar images and texts are close to each other, right? The second challenge when developing these representations is that images and text themselves, they follow very distinct generative processes. And many-to-many mappings naturally emerge between the image and text domains. That is, you take an image, you can have many captions that can describe it. And similarly, you take a caption, you can have many visual representations which can be described by the text, right? So we need to encode this heterogeneity of the diverse distributions and capture the multimodality in the latent space. Now, the diversity captured with our current models in the latent space is limited to that available from the pair training data. And thus, the third associated challenge that we discovered is the availability of your training data. Now, when you collect data through human annotations, the data is sparse, no matter how much you collect it. You cannot get a holistic representation of the entire world model, right? So the underlying multimodality of the conditional image and text distributions can better be captured with the more data that you have. However, collecting this data is, as we all know, is very expensive and also very noisy. Now, for many-to-many mappings, it is important to capture domain-specific variations of images and text in the latent space when learning complex joint representations. The latent space should be modeled such that it contains latent dimensions that model the semantic information corresponding not only to the shared information, but also the domain-specific variations in information. For example, the diversity between the image and the text distributions, the different visual and the textual styles, they can be encoded in the residual dimensions. It should be such that you can have the shared variables and also the variables which are specific to images and the variables which are specific to the texts, right? So you don't lose any information for the joint distribution. Yeah, so what we want to do is capture the domain-specific variations in the latent space to address the challenge for many-to-many mappings. Now, what prior work generally does, or what much of the work till today, what they do is they take the image and text distributions, they encode them in the shared latent space, and they enforce a Gaussian prior if they are operating in a generative setup. So what are the limitations? Now, they are not preserving your domain-specific variations is one, right? Because you are losing the information as we already discussed. Second, when you enforce Gaussian priors on multimodal distributions, they act as very strong regularizers. And then you lose a lot of information, right? And it is very difficult to train such models. For example, you see in the graphical model, what they do, they take image variables like xv, you have xt, which is the input text distribution. You encode it in the latent variable zs, and then you are enforcing a Gaussian on this latent zs. So basically, you're losing the domain-specific information, as well as you're enforcing a Gaussian, which results in very strong regularization. How do we circumvent this, right? Now we want to capture the heterogeneity of the input distributions by modeling the latent space such that it contains latent variables that are shared across the two domains, denoted here by the latent variables at S. And you also want domain-specific variables, which are z prime v and z prime t, corresponding to the text, image, and the text distributions. Now, given the shared variable for supervised learning, the domain-specific variables encode the residual domain-specific variations, right? So they are supposed to include the variation excluding that from the shared information. For example, look here. So we have two images. One is that of two images of a dog sitting on the bench. The variations here in visual style can include the type of dog, the pose of the dog, the type of the bench, the location of the bench. They are all variations in your visual style. And the variations in linguistic style include, for example, one sentence can be written in your modern English, a dog is sitting on a bench, and the other sentence can be written in Shakespearean English, right? I am not going to read that. And, right? So this is what we want to encode. How do we do this? So first thing, we maximize the elbow on the data log likelihood of the joint distribution in a variational framework. Looks like a variational autoencoder, right? Very much so, but with the joint modeling of images and text, right? So what is it? It's an expectation on the log likelihood. In this lower bound, you have an expectation on the log likelihood of the data, the joint distribution, given a latent variable z, which is drawn from a posterior q theta. And then there is a divergence term, which is an expectation again on your posterior and takes the difference between the log likelihood of your latent distribution and the posterior distribution. What does this entail? So the prior over the latent variables will factorize as the prior on the shared latent space, denoted by P phi S. And we have conditional priors, which are domain-specific conditional priors, and they are denoted by P phi T and P phi V, which are conditioned on your shared latent variable, ZS. The variational posterior also assumes a similar factorization, where Q theta 1 is the posterior over the shared latent variable, and is denoted by ZS and is conditioned on the input distributions. The conditional posteriors are conditioned on the shared latent variable as well as on the input distribution, their input distributions respectively, right? So this is the method, like the framework, the variational framework as it should be. Now let's translate it to the neural network architecture. What does it look like, right? So for image and text distributions, you have a variation, you have an image and text encoder and decoder. So those are your domain-specific encoder decoders. And what you do is for each of the domains, you encode them into the latent space to generate variables Z prime V and Z prime S. And for the text, you will have ZS and Z prime T. Now, on these latent variables, we enforce normalizing flow-based priors such that your latent space is inherently multimodal. First, what you do is you encode the shared latent variables using an invertible neural network, right? And you assume a Gaussian prior on that, assume a uniform prior on the shared latent variable such that you can use a mean square error or any supervised loss without KL term. And for the domain-specific variations, you use normalizing flows conditioned on this shared information, and they are mapped to a base Gaussian distribution, making it easier to sample. And these can be computed in closed form using the change of variables formula. And during generation, what happens is you take an image for image captioning, you take an image, you pass it through the image encoder, you take ZS from that encoder, you pass it through your invertible neural network, you will get ZS in the textual space. Then conditioned on this, you can sample Z prime T to generate diverse captions. So let's have a look at the results. So here are for a given image, instead of generating just a single caption, you can generate diverse captions. And we validate this method on the COCO dataset for image captioning. The captions generated with our approach show diversity. For example, in information, in the first sentence, you have 2 elephants near the river, and in the second one, you have it near the grassy area, right? And this is also reflected in quantitatively in the accuracy and the diversity scores. So for accuracy, you consider the standard BLEU score and the CIDR score. And for diversity evaluation, you look at the uniqueness in the n-grams, you look at the novelty of the sentences that is generating, you look at the M.BLEU score, which is the mixture score of all the BLEUs for diversity, and you have div1 and div2, which are the n-gram diversity scores. And you can see that our approach outperforms by large margin the prior work, which actually enforces the Gaussian priors in the latent space for image captioning. One thing you notice is that our model can do bidirectional synthesis, right? So given a text, we can also generate images. And for text to image synthesis, this is how our results look like. So for a given text, a skier is skiing down the snow slope. We can generate diverse images. These images might not look that great to you because the decoder here used is a standard DC GAN from 2016, not a diffusion model. But if you replace the decoder by a more expressive generator, for example, a GAN or a diffusion model, you can definitely get better results. But importantly, we want to evaluate how good were the latent spaces that we learned, right? So when you look at the IBOM metric and the LPIP score, we outperformed the GAN-based models by a large margin there. For example, if you look at the state-of-the-art attention GAN and you look at LNFM, which is our model, so when you look at the latents in the test data, which are closest to the image, right? And you then try to generate the image using that latent, you can see that our model has better captured the edges of the bear, right? So it can effectively learn this image semantics condition on the text, right? So this was about the many-to-many framework for bidirectional synthesis. I will now address the second challenge that we saw was that of limited paired training data. This approach, while we have applied for the captioning task, is also applicable for other tasks such as VQA or reasoning, just it is very generalizable and you can use it for various image text tasks, basically, right? So the variability in human label captions is limited in the existing data sets, but we observe that similar contextual information also exists in other scenes, even when the objects present are not the same. For example, in these two images and text, suppose I remove the object information, there is some similarity in the contextual information between the two. And we aim to leverage these variations in textual descriptions by exploiting the textual similarities in images for the task of image captioning, right? So you can introduce more diversity with you can capture the multimodality of the context better. So existing methods, including our previous work, we encode the conditional distribution given the image, and we cannot leverage these variations in the descriptions. Thus, the amount of diversity that we could capture was limited. So what we do is we introduce a context object split latent space to encode the contextual information independent of the object information. How do we do this? For this, first, what we do is we take our annotated pair data, we remove the object information to get the context description as shown here by YM. Following this, we learn an image context embedding space through a contrastive loss or a max margin hint loss. And then for any given image I prime, we can retrieve the contextual descriptions from this image context embedding space to provide the signal I prime and YM for pseudo supervision. Now, equipped with this, we can formalize our COS-CVA framework. So COS means context object split, right? And it's a conditional variational autoencoder framework. So given an image, first we retrieve the contextual description using our image context embedding space, and we encode the posterior Q theta M, independent of the object information. Then, for any paired training data, we extract the object information directly from the caption and encode the object information in the posterior Q theta O, right? Then we can use the latent variable Z, which is a concatenation of ZM and ZO from context and objects respectively, provide it as a condition to our top-down attention LSTM to generate diverse captions. What is the advantage of this now? So in addition to this standard setting, suppose we want to generate a caption for an image where we have never seen the object before, right? So we can train it on images with novel objects without having any pair training data. We obtain the object information from the faster RCNN, which gives rise to a weaker posterior now, denoted by Q theta O. And since it is a weaker posterior because the object information does not come directly from your ground truth captions, right? And the target caption and the context is retrieved from the image context embedding space. You still get this latent from a weaker posterior ZO and also from ZM. You concatenate it, and your model can now attend to the appropriate regions to generate a diverse caption, right? And this caption contains the mention of the novel object. Let us have a look at the results. So our results for diverse captioning generate more diverse captions containing contextual information like curled up on a piece, which never existed in the training data for CAT, actually. This is reflected also in the accuracy and the diversity scores. So you can see that in terms of the accuracy, we definitely perform better because we are using additional pseudo supervision signal. But if you look at our diversity scores, we also do much better in terms of n-gram and MLU diversity, which shows that we capture these novel contexts from the different contexts within the data set, right? However, for novel, the performance is lower compared to our previous work. This is because we have used a lot of information from our training data, and it tries to use that context within your data set, right? And thus we can see the conclusion from this slide that we have more diversity from the contextual descriptions. And if you look at the results on novel object captioning, now this couch was never there in a COCO data set, right? So we look at a caption for this image, and you can see it can attend to the right regions. And it can generate captions which are meaningful and contain mentions of the novel object. We compared it quantitatively with the prior work, which explicitly works for novel object captioning, but for generating single captions. And here our F1 diversity is at least on par or slightly better than prior work. But to assess it better, we look at the CIDR score and the F1 score with varying number of samples. So does this result hold no matter how many samples you draw from this conditional distribution? And we find that, yes, our model can generate captions, all of which contain mentions of novel objects and also are very accurate, right? So it can effectively generate diverse captions for images with novel objects. Yeah, so this was about my work with deep generative models that I did during my PhD on multimodal representation learning. And now I will shift gears towards diffusion models. So in the beginning, I just introduced the three kinds of generative models, right? So where do you place these generative models are? So let us have a look at VAEs again. So VAEs approximate the data log likelihood of the distribution, right? And so do diffusion models. So diffusion models are also a kind of variational autoencoders. They are variational models, and they also transform from a noise distribution to a parameterized data distribution. So the idea is that you have a noise distribution. You start from the noise distribution and you can denoise it over n steps to generate your final data output, right? So so the theory of it also belongs to this class of variational models using the evidence lower bound, right? So nevertheless, let's have a look at the work that we did in this direction, which is Make a Story, which was at CVPR 2023. It's called Make a Story, Visual Memory Conditions, Consistent Story Generation. And the goal of the work is to generate a sequence of illustrative image frames with coherent semantics given a sequence of sentences, right? So we want to generate a story of illustrative image frames given a series of sentences. And what is desirable is that we want coherent semantics, right? So we want a flow in that story, as to say in layman's language. So we want to generate temporally consistent stories based solely on the linguistic storyline. That is, we want to maintain also the references, or we want to resolve these references as we do in the textual space, right? For example, if you look at the storyline here, so in the first sentence, we have Wilma and Betty, which are the two characters we are talking about in the story. But as the story progresses, we refer to these subjects and objects as pronouns, right? So they are references, like she turns to grab quills from a porcupine. Now, who is the she being referred to here, right? These things are important for a consistent story generation. We want the stories to be consistent with respect to these subjects and as well as the background appearance, right? So we do not want the background to change across the frames randomly. And here the challenge is that generative models like diffusion models, they are very good at generating high quality visuals, but not so good at maintaining consistency. How do we do it? So we take the standard latent diffusion model and we propose a deep generative approach with autoregressive structure, given a textual storyline characterized by a sequence here of M sentences. The goal of the story generation now is to produce corresponding frames that can visualize the story. So we will extend the latent diffusion models to this task by allowing them to generate multi-frame stories autoregressively for a given texture. So the latent diffusion models, given a textual condition, they use a cross-attention layer to capture this conditioning for generating an image. Now, to capture the spatiotemporal interactions and frames of sentences in a story, we introduce a rich conditioning structure that takes into account the current sentence, as well as the context from the previously generated frames. And for this, we introduce a memory attention framework, right? So as you can see, the generative process for a frame ZM for T steps of diffusion factorizes as shown in the equation. So it is conditioned not only on the current frame, and not only on the current sentence, but also on all the previous sentences, right? And how do we achieve this? It is through our memory attention module, which takes the current sentence of the frame as query and the previous sentences as keys to weigh the values, that is the representation C, right? Note that this is unlike your standard key query value attention mechanism where your keys and values generally come from the same domain, right? This visual memory now allows us to incorporate the character background consistency and resolve these textual references as needed, resulting in the improved performance. The final output of this attention mechanism is the aggregation of the standard cross attention and the memory attention. As you can see in this figure, we show how the memory progresses with your number of frames. Like as your story progresses, we take the entire context starting from Z0 to ZT, right? Z0 to ZK, right? So you look at all the frames and all the previous sentences. Now, to validate the co-reference resolution and character and background consistency, we extended first the existing data sets to include more complex scenarios, like we included more interactions and also replaced the explicit mention of the subjects by their pronouns, right? And to measure the consistency, we also introduced new evaluation metrics like character accuracy, character F1, background accuracy, background F1, and the FID scores. And when you compare it to standard latent diffusion model, and you try to generate this story using a standard diffusion model, you can see that it cannot maintain this character background consistency across the frames. This is also seen qualitatively in this figure, right? So if you look at frame number 3, even frame number 2, right? So there is a loss of concepts from the latent diffusion model, right? So you can achieve improved generative image quality and character consistency with this autoregressive structure using this memory attention module. Other interesting applications of this are that you can generate diverse frames for a single storyline, obviously because this is a generative setup, so you can sample multiple frames, but all those frames lead to different stories, which is very visual stories, which is very pleasing. So you get diverse frames from a single storyline. And also what you can do is you can branch the storyline. So you can start from a text, and as you change the captions for the following sentences, you can also generate diverse frames. So you can have different endings starting from the same frame, for example, right? So this is one more application. So to conclude this talk, the technical contributions in this work were with respect to learning of multimodal representations and the diverse synthesis. In the first part, we focused on multimodal representations of images and texts in the latent space in a deep generative variational framework. Our semi-supervised approaches allow for better cross-domain mappings and enable many-to-many mappings. We exploit image text representations apart from those available from the paired training data, and propose context object supervision in the cost latent space, which allows for novel object captioning, which is the first work in the setup of diverse caption generation. And in the second part, we looked at consistent story generation in the framework of diffusion models, where we proposed a memory attention module to capture better spatiotemporal consistency. So that is the end of my talk. I thank you all for listening, for your attention, and I'm happy to take questions now.